We did a presentation for the C++ meetup in Dublin about this a couple of weeks ago, and our video failed, so I'm doing it again. So thank you for everybody for actually listening to me and coming to hear me talk about this again. So just to get started then, so I'm going to just talk about exception handling, which is probably something that most people that write C++ have some sort of awareness of. This is my little basic example program that kind of has a function main that calls a function f, that calls a function g, that calls a function h. And there's this h function randomly throws an exception. F catches it, and then G is this kind of innocent victim bystander in the middle. So I kind of refer to this code or variants of this code a bit through the.
Peter, they're telling me that the audio isn't great. Could you speak a bit slower?
Okay, so this is my sample program that I'm going to use to describe the exception handling mechanisms. So we have these functions f, g, and h, and f calls g, calls h randomly throws an exception, and f catches it. G is this innocent bystander in the middle, and we can see that G uses this RAI pattern to initialize and destroy the variables in it. So the normal exception handling, I mean, why do we use exception handling in the first place? Is that it keeps all of our kind of happy path code together. There's no error handling at all in this code. I mean, it's just nice, clean, start to finish. In the normal case of events, this is what happens. The error handling is all kind of captured down here in these catch blocks, and the more you use this RAI pattern, the more your error handling is kind of grouped into the same place. And in general, the RAI thing again helps because the cleanups happen implicitly in the code without you having to worry about it. Okay, so this is kind of the why we do it. But I mean, when I started looking at exceptions before when I was learning C++, I could generally kind of work out from the language what the compiler would do to generate code for it. You know, you can see how templates might work. You just generate much more code. You can see how loops and iterators and conditionals work, but it's very hard to work out, or I found it very difficult to work out in my head, how the compiler could actually generate code to handle exceptions. So we're going to look at two main ways this happens. That's the other reason that about exceptions is that if you throw an exception, it should be pretty much free in order to if you don't throw an exception, there should be very little cost in the system to managing the whole exception mechanism. So the how is basically using set jump long jump, which is a very old non-local transfer of control operation from C back in the 1980s, probably 1970s. And we're going to have a look at how we can use that to implement a form of exception handling. And we also look at the way dwarf does it and the dwarf information and how those tables kind of fit together. So set jump long jump is used by GCC on systems where it has no other choice. So I think that's at the moment things like the MinGW Windows compiler, and pretty much most other GCC targets are things like Linux and various Unix systems that use some form of dwarf or ELF for their binary representation. Okay, so the first thing we do is talk about set jump long jump, and this is kind of poor man's exception handling for C. So if we look at kind of our C program over here, we can see we've got something similar. We've got F calls G, calls H. G has these kind of cleanly structures here. Sorry, this is C++. So we have our RAI-based structures here, and then we have a long jump function here. So we call set jump initially with a jump buffer, okay? And set jump is a bit weird in that it returns twice, okay? So the first time set jump returns is like the normal case where we go into F and we call this if set jump buffer, it returns 0 to us. And we invoke G, and we go through our normal exception handling logic, okay? So as I say, first call returns 0. So what it does with the buffer is it stores the state of the machine as it is at the point that it invokes set jump. So this includes things like the stack pointer, the instruction pointer, the general registers, potentially floating point registers, everything. So we then go to call G, which eventually calls H, and we end up in this long jump function, okay? What long jump does is it restores the machine state from this buffer back into the machine. So it's a very heavy hitting hammer in that it changes the existing state of the machine. So the stack pointer just jumps from where it was down to where you want it now, or down to where it was originally. The return register, say for example, EAX in the case of x86, which is the return value of a function, would be replaced by something else. And it organizes for the EAX value to be replaced by this 1, was the second argument to the long jump. So what appears to happen is that long jump actually, or set jump returns twice. It returns back down here. okay? And the effect is that we just discard all of the state that G had built up and any potential state H had built up or anything in between on the stack. So this has the effect of kind of cleaning up our stack for us, but we don't actually get the cleanup of the individual variables on the stack. There's no RAII and there's no way of cleaning anything up in between, okay? Anyone got any questions online there? Good so far. Okay. So we can kind of improve on this by just kind of chaining things together. So what we do is we kind of create a little small API. This is kind of a nutty example of how we might do it in C. And what we do is we have a struct. Here's our RAI structure that we want to clean up, and our constructor. And then we give an indicator of how we actually want to clean up this structure. Okay. So what we do in our try function. Remember, this is C rather than C++ now, so I can have functions called try. And this basically will return a jump buff to me, and I can do my set jump work here. Call G, which calls H, which calls whatever. And this is pretty much the same as the original set jump case. But now when I'm in G, what I'm doing is I'm building up this set of cleanup handlers. So if I know I need to clean something up at this point in the code, I can say, okay, clean this up. And then as I destroy the things, I can remove these cleanup handlers. Okay? So now when I throw an exception up at this point, I have this kind of global state that I can look at, our per thread state that says, here's the list of things that I need to actually destroy as I go down from my long jump point down to the original set jump call. So I get the opportunity to clean up all the data that's being that I need to clean up in here. So if I'm at this point here in the code, I'll be cleaning up both of these objects. Sorry, when I'm at this point in the code, I'll be cleaning up both of these objects because I've got two handlers pushed onto the stack. Okay? So this is pretty easy to implement. You can see a really kind of basic header file that implements it here. Our cleanup handler is just a void pointer to some data and a function to call. The exception state, which is allocated by the try, is something looks something like this, just has an array of cleanup handlers. I have my jump buff and then just a length of the cleanups. And then when I eventually call an exception, I just store that information here. Okay? Now, the implementation is very simple as well. In this case, what I kind of do is I can kind of create these objects in kind of on the stack as I need them. What will generally happen if a compiler is to implement this, it will use the machine stack in order to implement. Okay, it'll use the machine stack in order to implement the actual memory allocation. So what I did was I went back to kind of find a compiler from sometime in 2004. And this is FreeBSD from 2004. And what it actually generates. I'm not going to spend too long looking at this H function that does the throw. This kind of, you can see it calling this get EH context, which gets this global state for the exception machine. I'm not going to look at H too much, but if we look at G is the function that has to do the RAI work, and you can see what it does in here. It calls get EH context, stores it in EDI, and then as we walk through the code, we can see that it constructs this clean me object, and it builds up on the stack in this EBP points. It builds up some information which includes a pointer to the object itself, the way we need to destroy it, and then a chain for the next item in the chain. So this is actually what we were doing previously in our own nutty implementation, where we were building up this kind of list of handlers to run. So this is actually a real compiler doing it. I don't want to go too much into the assembler output here because it's just going to get confusing. But you can see that real compilers do this. They will generate code to register the cleanup handlers and will run them when the try catch happens. You can see, like I say, and again, we can see that there's a huge overhead in terms of actually managing this. Even if we don't throw an exception, we still have to do all this work regardless. Okay. Our function that throws the exception, again, I don't want to get too involved in what it's actually doing, but we can see a little bit later on in it, before it actually calls this G function here, above here, we can see that it pushes, it gets hold of this value here, which is just a label. And if we look at this label down below, L494, just further down again, let me try and find that label again. So here's the label it uses, it's 494. And down here you can see that this is actually the exception handling code, okay? So we can see that this is, it's not actually calling setJump, but it's doing effectively the same thing. It's maintaining, it's holding on to machine state so it can be restored later on, okay? So that's how setJump, long jump exception handling works, basically. And there's a few things really wrong with it. The first is that the happy path is affected. There's a huge overhead, or a noticeable overhead in the case that you don't throw exceptions. And then the other problem is that as we actually record exceptions with the try block, we need to maintain this machine state. And that's our set jump call. And the set jump kind of block that we use is quite large. I mean, the set jump blocks, I think, they're 200 bytes on 64-bit, 156 bytes on 386. So they're non-trivial amounts of memory that you're using every time you do a try and a catch. Okay? So that's pretty much me on try-catch exception handling. So it's a good time if anyone wants to butt in and ask questions about it. I mean, what we do is we kind of build on this from here and say, okay, how can we improve on it? So if there's any lack of understanding, shout. All right. Okay, so the next thing we do is we kind of start to do like a tabular-based approach to doing the same thing, and we make a few observations. So we say that if we take our function g here, which is this innocent victim in the process, which is the one that's kind of paying the penalty for the exception handling without actually using any exception handlings, we can see that at any point in the code here, so if I'm kind of right here, just before I've kind of constructed this clean me object, I know that if an exception is thrown there, I know it's impossible to happen, but should an exception be thrown at this point, I have nothing to do. I know that I've gotten past constructing the here object. If I'm here, then I have one object to clean up. So if h throws, I need to clean up the here object. And I know if h throws at this point, I need to clean up both of them. So I know lexically at what I need to do in that particular function, based on what the current location in the function is. All right? So that's something I know at compile time. Okay, so what I can do is I can create a table that is keyed by the program counter that I'm at. So the program counter in G, so as G calls H, it will have its own program counter at this point, and I know at that program counter what I need to clean up, all right? And for any one function, that gives me everything I need in order to restore, or in order to do the cleanup, so the catch handling for that function. And that works for the catch blocks as well. So I know if I'm in G here, or if I'm just calling G from F, that if G throws, then I know I need to run this exception handling code, or potentially need to run this exception handling code. All right? All right. So the great thing about this is that it's pretty much, there's no cost involved for the happy path. If you're not throwing exceptions, then you don't have to worry about it. All you need to do is, when you do throw the exception, you have to work out what the instruction pointers were at each frame on the stack. And then from that, work out what you have to clean up for that function. All right? The problem with it is that because we've got all these tables and we haven't built up this structure dynamically, it can be quite expensive in the case we do actually throw an exception. And we're going to have a look at what that actually entails, because I think when you think about exception handling, I know people kind of are told that there's a huge cost to throwing an exception, and you take it on faith that this is the case. But when you actually see the amount of things you have to do, it gets quite scary. Okay? So we're going to have a look at our table. So if we think about what the table might look like, we have a table pretty much for each function. And the table is a set of entries. And the entries are basically the offset of the first instruction that we're interested in the function. So this is the range. An offset of length gives you this range of instruction pointers within the function that we're interested in. The address of a landing pad. So if we think about our function G here, on this side over here, we can see that G has our two objects, but the compiler will generate extra code here for doing the cleanup code. Okay? So in order to do a cleanup of here, there, or both of these, there will be extra code added to the function afterwards. So this does pad out the executable a bit, but there's no impact other than the fact that the executable gets larger. So as well as having the address of the landing pad instruction, we also get some information about what we need to do should an exception be thrown at this point for each individual exception type. So we kind of have this kind of table of actions that's a list of things that have an indicator of what type we're interested in. And these are just a list of C++ type info objects. So we can say that we can handle different exceptions with different code. And then eventually we have a type filter of 0, which means this is just cleanup code. We'll get to do a little bit more of this later. I'm not going to dwell too much on the handling different types of exceptions because it's pretty much an extension of the basic mechanism. Okay. So the action information is the type information. So what happens as well is that the compiler with each of these tables will associate what's called language-specific data. Okay. Sorry, the table is associated with what's called language-specific data. So we can see when we have a look at the actual code that gets generated, you'll see that the pseudo instructions that associate this table with the function. When we get later on, we'll actually see where that binding takes place at runtime. But we can have a quick look at it here now. Hold on. So this is our somewhat messy slide, but we can see this is the compiler output for our function G. Okay. You don't need to worry too much about the individual instructions, and the colors will kind of guide a little bit. Here's our original source for G. And here's the table that we generate that we looked at earlier on. So this data here is just a representative of this previous table that we looked at, and we can kind of look at it in detail here. So if we think about entering G at this point, just before G, this here object is constructed, there's nothing that we need to clean up. And this red line here in G corresponds to this code that's in red in the assembly output. And you can see it's actually calling the constructor at this point. All right. We also see at the start of the function that we've kind of associated this CFI personality pseudo opcode, and that gives a reference to this function. So this is a function that's defined in the C++ runtime. We'll have a little look at this later on, but this is just saying really to the runtime, to the system runtime later on, that this is a C++ function, and this is how you need to handle exceptions for this function. And then we associate this table here with it, with this LSDA from this opcode here. So this label here, you'll see, is the same as this one here. Both sides of this are in the same file. So this is just output in the same .s file from the compiler. And we know, so the G is now associated with this table here, sorry, with this table. All right. And we can see the individual fields. So for the red block of code here, for that red block of code, we can see we have labels giving the start and the end. So it's LEHB0, LEHE0 here. And these correspond to these labels over here. So this chunk is encompassing this red piece of the assembler output. Okay? Now in this case, we've no landing pad, so we've no code to run in this case, and we've no action to run because we've nothing to clean up at this point. Right? But as the code advances through to this kind of green section of code, which is just where we call H here, you can see it down here. So at this point, we have a start, which is this LEHB0, going as far as LEHE1, or B1 and E1, which are these labels. So this is kind of encompassing this chunk of code. And we're saying that if something happens in this zone, we need to call this landing pad. The action 0, because this is a cleanup function. There's no actual catch blocks here. This is only for cleanup. Okay? And this orange chunk here corresponds to this code down here. Right? So we can see what this chunk of code is doing is it's just destroying one clean me type object, and then calls unwind resume to continue exception handling processing. All right. And again, once we progress beyond the green piece, we're in this bluish piece. And now our table entry says between these two chunks of code, which is again, these chunks, you need to call this landing pad, L13. And this L13 landing pad does the same thing. It actually cleans up two different objects. So it cleans up first one object, then jumps to L11, and then cleans up this object and calls unwind resume. So this is saying that for any one particular function, again, we know that should we get, at any point in this code, if we know that we have hit an exception at that particular point in the code on the stack, we know what we need to clean up. Is that clear?
If you compare, not exactly the same, but if you compare the gray section, the regular cleanup with the yellow section, aren't they the same?
So you're saying that this chunk here, which is where we actually just do the natural fallout of the function, is very similar to this, right? So
it's not exactly the same, though.
they're very similar. And I mean, you could potentially have the compiler
just produce labels from that section.
It potentially could. I think the idea is as well that this code can go into a separate section that is not necessarily, it may be on a different page, so that it doesn't get paged in as quickly. I didn't put the compiler optimization up very high because it makes the code very hard to read. It potentially does. I mean, I could experiment with it and see. But yeah, I mean, yes, the compiler will do weird things. It's a guarantee that the compiler will do weird things on it. But as I say, it's just showing the intent here is that we have our table that says for this piece of code, this is the landing pad you need to run. All right. It would have been much harder to explain that as well. Okay. So that's kind of our table. So we've talked about how we know what to do in the cleanup. Okay. But we haven't talked about what happens. I mean, if H throws an exception, we need to find G. We have our stack, we have a runtime stack of functions calling functions. So we need to basically get from H, and we know what H has done. Now we need to go back and find out what functions have we called, and how do we find the enclosing try block. All right. It was easy for the set jump long jump case. We didn't have to care about it. We just discarded the stack and did all the cleanup routines we needed to run. But now, because our table is based on the instruction pointers in those frames, we need to find out where we were in those frames. And then from where we were, we go through our table and work out what we need to clean up. Make sense? Right. So just to give you a quick overview of how stack unwinding works. So if we take a function like this, the standard kind of C model for a situation like this is we'll start off that the runtime will pass arguments to main by pushing them on the stack. So argv and argc get pushed on first. Then the C runtime will call into main. So the call instruction will generally push the return address of the function that you're in onto the stack, right? And then advance the stack pointer. So our stack pointer comes up, and the return address back into the C runtime is now on the top of the stack. The next thing that happens is the function that we entered will push its own local variables onto the stack. Our main has none, so it doesn't do anything here. It'll then call F, and it'll push any arguments to F onto the stack. And then we do the same thing. Our call instruction pushes the return address onto main. Local variables in F then get pushed on. F calls G, pushes the arguments onto G, or pushes the arguments for G onto the stack, calls it, leaves its own return address on the stack. Then we up into G, and G is our innocent victim function here. So the first thing it does is push its local variables, which are the here and there variables. It calls H, and then eventually we get to the point that we throw our exception up the top, okay? So our problem now is, from H, we need to basically look under here and see all these return addresses and all of these variables so we can clean them up and get pointers to them, right? Okay, so we're gonna look at the easy way and the hard way of doing this as well. So in the same way that we were doing our set jump, long jump, exception handlers and recording information, what we can do is we can use a machine register to store the actual address of each frame. So what we do is we have a frame pointer register, and then on entry into a function, we copy the stack pointer to the frame pointer. I'll make this a bit more visual later. And the new frame pointer then, so we push the old frame pointer and copy the stack pointer to the frame pointer. So what this means is that we have a placeholder on our own stack to say this is where the previous frame pointer is, and we have a pointer to our own stack frame. Okay, I'll make it a bit visual in a second. x86 uses there's an EBP register or BP register, depending on 16 or 32-bit, that's used for storing the frame pointer. So there's actually instructions on the CPU that help you use a register for a frame pointer. So enter and leave are kind of there as standard prelude functions to set up a standard stack frame. Okay, so just to show how it looks, we start off with our EBP, which is our frame pointer, and ESP pointing somewhere randomly down in the stack. We do our standard call again, where ESP or the argv and argc get pushed onto the stack. Then what we do is we do our call, which pushes the return address again onto the stack from the C startup into main. And now the first thing that happens is what main does. It makes a copy of EBP, which is down the bottom here, pointing to somewhere down here. It makes a copy of it and puts it onto the stack, and then points EBP at that copy, right? So you can see we've got EBP, old EBP, and then down here we've got the old, where EBP used to be down the bottom, okay? And this continues on as we push arguments onto the stack. The stack pointer can move up and down within a function, but once we call into a new function, the EBP base pointer moves up. So now we have, at any particular function, we have a well-defined point to say this is our stack frame, all right? So when I get up to my G function where I push my arguments onto the stack and then eventually end up calling into the H, which throws the exception, H can look at the value of EBP and say, okay, this is my frame pointer. And if I look at the value of EBP here, I can see the previous function is here, and its return address is just below me here. And then I can walk from this point, I can walk down to here, and I can find the next link in the chain and the return address back to main, okay? So I have a linked list, basically, of instruction pointers all the way through the stack. And this allows me to unwind it and say, at this point, I know that here's my return address for G. I know where I am in G. I could be either here or here. Am I this point or this point? So both invocations of H will have a different return address back into G, which will affect how my cleanup works when I start looking at my table. All right. Right. So just to show you that this is true, this is a modern 32-bit compiler output, okay? And we can see that main does things like, well, maybe a bad example, let me go up the top here. So here's clean me calls push EBP and move ESP into EBP. So normally, well, often this is the way it works. We can also use an enter instruction to do this. I think enter probably takes more clock cycles or whatever, so it's not generally used. You can see that the leave instruction is used here, which does the opposite. And then you can see on some other functions later on, I think main might be one of them, that rather than using the leave instruction, we just do the pop of EBP, okay? But this is, again, just doing the same thing. I mean, depending on the actual assembler, what the compiler wants to do, it'll organize for the stack frame to be set up in some way. But there's a standard part of the ABI that the stack frame looks like this. So if you write a function in a C++ program that needs to run on x86 Linux, it will guarantee that the stack frame is set up like this normally. Static functions may not do this. There's compiler flags that you can throw at things like f-omit frame pointer that will stop you seeing the frame pointer. All right. So the f-omit frame pointer basically stops you using this register, so it saves you the register, but you pay the penalty of not having easy stack unwinding. Okay. So I think I've missed a slide here somewhere. Okay, so what we can do is the problem with this is that we're using an extra register in the machine that we could be using for something else. We're generating code in every function that manipulates the stack, which costs us, and it just generally makes things slower. And again, the only time we actually need to do this stack unwinding is in the event that we have an exception thrown. So we're paying a penalty for it in the normal case that we don't normally have to take. So we can kind of look at it another way. So with our set jump, long jump exception handling, we were kind of making note of the fact that at any particular point in the code, I could make inferences about what I needed to clean up based on the instruction pointer. So as I say, we can save the instructions to stack base in the machine register by having a table for each function again, okay? And what we do is in each row of our table, we say, how do we calculate the content of the register in a previous function? So for my function h, I build up a table, and my table basically says, if I'm at this point in the function, here's how I restore the state of the previous stack frame, okay? This gets a bit more visual again, which makes it a bit easier to understand, okay? And each row of our table is a vector designed for this point part of the instruction. In order to get from this frame down to the previous frame, you need to do this, and you need to kind of replace this register with this value, etc. Okay? There's two special values in the table. There's the call frame address, which takes the place of our frame pointer. And the call frame address is pretty much defined for any architecture we care about to be the stack pointer as it was in the calling frame when it called us. So if we think about our stack pointer just before we entered our new function, so when, say, G calls F, the stack pointer is the stack pointer as it was in G, right just before it hit F, or right before the call instruction. All right? And we also have this special return address register, and the return address register takes the place or is kind of an alias for the instruction pointer at that point. Okay? So here's our annotated assembly language again. Again, don't be too caught up on the instructions themselves. So the stack, as we enter into this G function, we have our pointer here to the arguments we passed into G, and then the stack pointer, which is pointing into the return address back to F. So right on entry into G, this is what the state that we're at before we do anything else. So right at this point here, as we come in here. All right. So some of these instructions, as we walk through, will affect things inside. But let's have a look at what our table looks like. So our table pretty much has an address, and then a state for each register. The registers are just treated as with numeric indexes. So there's register 0, register 1, register 2. Those registers then, these registers in the table are kind of generic platform independent concepts. And then each platform will map each register index to a specific register. So RBX on x86 or x86-64 is actually register 3 in the table. There may be many more registers. And then we also have entries in the table for the CFA, which is this frame pointer replacement, and the return address, right? So the first row of our table in G is easy enough because it says that the CFA is at the current stack pointer plus 8, which is just down here. Remember, the stack grows downwards in memory in x86. So what's under us on the stack is at a higher address in memory. Okay, so this is our CFA. Our CFA always has to point to this point here in the stack, all right? And our return address is at the CFA minus 8. So again, the CFA, if we think of our CFA as being here, then 8 bytes earlier, we have this return address, okay? So this is pretty much telling us how we could actually unwind the stack if we're at this location here in G. In the same way we used the frame pointers for it earlier on. We're just saying if the instruction pointer is right at this point, this is how we do it. The next thing we do is we execute this push instruction, which pushes something onto the stack. It pushes 8 bytes onto the stack. And this is a 1-byte instruction, so it addressed G plus 1. First thing that's happened is the stack pointer's moved away from the CFA. So our CFA now is now 16 bytes away from the stack pointer, not 8 bytes away anymore, all right? But also because we've pushed a register onto the stack, which was ORBX, we now know that if we want to get the ORBX value from the previous frame, we can look at it at CFA minus 16, right? The registers with the dashes here are basically registers that are unchanged or undefined from the previous call frame. All right. So next thing we do is we reserve some space for local variables, which is taking 16 bytes off the stack pointer. This is a 4-byte instruction, so we advance 4 bytes through. ORBX hasn't changed, nothing else has changed. But now we've gotten our stack point, our CFA is now 32 bytes away from the stack pointer. Okay, nothing else has really changed. So we continue on to this code without actually modifying any of the stacks, so that our way of actually unwinding at this point doesn't change until we get all the way down to here. So all of the rows in the table from this point are the same up until we get to this instruction here. When we get to this instruction, what it's doing is it's removing the stack space that's used for those variables. So our stack pointer basically moves back down to where it was. Our CFA moves back closer to the stack pointer now. And then our next instruction, which is popping ORBX, doesn't really have to affect this. And our CFA now is again closer to a stack pointer. And that's what the table looks like. So does that make sense? Our first approximation?
Is that table built fastly?
So that table is built at compile time, because all it cares about is the address in the function and what you need to do at that address.
I didn't get to what are those registers? Are not the CPU registers, are they?
So the registers, yes, the registers R0, R1, R2, and so on are CPU registers. So the format of the table is platform independent. So there is a mapping in the platform ABI to say that for the dwarf debugging information, register 0 equals, say, RAX. Register 3 is RBX.
How can I know the registers before running the code?
So you know that when on entry into the function, what you're trying to do is you're not trying to work out the values of the registers. You're trying to work out how you restore the values of the registers in the previous stack frame. So I know if I've just entered G, all the registers are exactly the same as they were before the call instruction. The only thing that's changed since the call instruction started to execute and when it finished to execute is my instruction pointer's changed to the new function, and the stack pointer now has been increased by 8 or decreased by 8, and I've got the return address on the stack, right? And that's what this reflects. It says the CFA, which is the previous stack frame, has jumped up, so I've pushed something onto the stack is what it's saying. My return address is just below me on the stack, and every other register is the same. It doesn't change. So for stack unwinding, you only really care about caller saved registers.
I got that.
Or call E saved registers.
Just forget how are those R0, R1, and R2.
So if you look at just R3, so R3 is just a good example to pick. So R1 and R2, R0 and R1 and R2 would behave similarly. So for example, if I don't need to maintain a register into a function call, so if I have a caller saved register, okay, so then some registers in the ABI are defined to be so that if I call a function, that register will be the same when the function returns. Some registers are defined such that if I call a function, I can't guarantee the value of that register when I return. So if I'm actually on a stack frame if I've been called by somebody else, I don't have to restore their value of, say, I can't remember the rules for it, but say that they don't care about ESI. So I don't have to restore ESI to get back to that stack frame. They expect to restore it themselves.
So the table wouldn't have the value of the register itself. That's what it tells them.
what it's doing is it's saying, if you look at the entry in the table here, it's saying you can find the previous value of ORBX
Okay.
on the stack, and here's where you find it on the stack. So on each row, I can say, here's how we find the value of the register. Yes, it's saying, so this is how you get to the previous state of it. Okay, and it's generally relative to the stack somewhere. You may find, for example, that one register could be stored in a different register. And in order to unwind the stack, you need to move from one to the other. And we'll see the details of how the table looks like in a minute.
Another point, this table seems huge because I have many bytes for each instruction, not for all them, but for many of them.
So Robert's point is that the table is huge, and the table would be huge, but we need to deal with that, and we'll deal with that in the next couple of slides. It is a massive table, but we can't represent it like this. Okay? All right, so where do we put the table, first of all? So this is dwarf unwinding. So dwarf is this debugging standard that came up for ELF images, and Linux and most other modern Unixes use ELF as the way they actually lay out binary files and loadable objects. And each ELF file it's a little bit like a tar file. It just contains a load of individual sections that you can access independently of each other. So the sections are normally for things like code and data, linker information, that kind of thing. But they can also contain things like debugging information. And the dwarf information specifically is carried in the ELF image. And the dwarf spec says where to find certain sections. So it'll tell you that there's a debug frame section has debug information in it. Okay? So this table that we've looked at here was previously stored in what's called the debug frame section. We've already talked about the fact that registers from call to call might be caller saved or callee saved. So the old spec would basically specify that you could restore the entire context. And this allowed you to kind of walk from stack frame to stack frame in a debugger. And as you walk through the stack frames, you could see the content of registers in stack frames lower down and higher up, as long as the compiler was able to generate the call frame information to find it out. For stack unwinding, we don't need all the registers. We don't need things like caller saved registers. We just need enough information to go unwind the stack. So it's the same table, but we don't have quite as many columns in it. Okay. So then this debug frame became this EH frame, which is this kind of simplified version of it. It has a few other optimizations to make it more amenable to processing at runtime for a program. So it uses relative offsets, so you don't have to relocate it and that kind of thing. All right. So we still have to address the point that this is a huge table. So we have to work out how to represent it in such a way that it's efficient. And this is kind of where we get to the point that there's some complexities in what happens when you throw an exception that you're paying a penalty for by having this cheap, happy path. Okay? So we can't represent a row of the table for every single instruction or every single instruction pointer in the executable. It'll be massive. So what we do is we have what's called frame descriptor entries. And there's a frame descriptor entry for pretty much each function. And then each frame descriptor entry, or a number of frame descriptor entries, can have a common information entry that they share. And this common information entry pretty much contains the first row of the table and some language-specific data as well. So we saw earlier on, we associated two things with these CFI pseudo instructions way back when we were looking at how we actually do the exception handling. One of them was the personality routine, which was this GXX personality v0. And the other one was the actual pointer to the LSDA table. If you remember that table that had the instruction pointers and where the landing pads were, that was also stored in the top of the function. So the CIE maintains the pointer to the personality function, and the FDE refers to the table itself. So each function refers to its own table, and then the CIE that they share in common will refer to the first row and potentially the personality function. Okay? So beyond that, the FDE has to expand that table out from that first row for all the other rows in that function. Okay? And it does this using pretty much a virtual machine. So we take our initial row from the CIE, and we execute instructions that are stored in the FDE. And these are kind of like virtualized instructions specified by the dwarf spec. All right? And each instruction can do a number of things. So it can update the disposition of a register. And that we saw it said that, you know, OR0 or OR3 is now stored at CFA -8. It can change where the CFA itself is. So we could say as we push something onto the stack, the CFA moves away from the stack pointer. And also, we can advance our virtual program counter to say, I'm moving down a number of instructions, okay? So what each instruction does is it modifies one cell of the table or moves us down a row or two, okay? There's some other complicated instructions that can do things like save the entire state and pop it off again later on. And they make it easy to do things like if you're jumping around a lot in the code, you can make it easier to restore the state. But remember that it's just really going through it instruction by instruction by instruction. It doesn't care about branches or anything like that. It's just a linear walk through the instructions of the function. Okay? So here's our G function again. And I've got some highlights in it. And this is pretty much the same that we're looking at when we're looking at the table. But here what I've done is I've dumped out the contents of the CIE and the FDE, okay? There's a command that you use to do that. So the CIE, first of all, is setting up our first row for the table. And it's saying that in this instruction here, we see that register 7, which is the stack pointer, is, the CFA is at register 7 offset by 8. So this is defining where our CFA is. It's saying that it's just under where the current value of the stack pointer is, right? Which is what we would expect as we enter into the function. We've just pushed our return address onto the stack. Our call frame address is just below us, right? And then the next thing we do is we say that the instruction pointer for the previous frame is at CFA minus 8, because it's right above us on the stack frame. Because that's what the call instruction did, it pushed it onto the stack. So these two instructions are really just specifying the behavior of what the call instruction did. Make sense? Okay. No questions for anyone? No? It's all gone very quiet. All right. Right, so we've got our first row of the table, which is on entry into G. Now, many functions will probably share the CFA, or the CIE. So this CIE is going to be the same for everything. The call instruction always does the same thing. All C++ functions are going to have the same personality routine. Oh, I didn't mention the personality routine is actually stored in this augmentation data. Remember, this table, this information is built for the debugger. Using it for exception handling is a bit of an extension. So there's this extension information. Now, this is before the linker got to have a go at the file. So this would actually have a pointer to a function, this GXX personality v0 function here, by the time it gets to the executable. And then we have a look at our FDE. So what our FDE does is it says for the first instruction is advanced location by 1. And this is just reflecting the fact that the push instruction is 1 byte long. It has an effect, so we need to record that effect. So the first thing we do is we move down to this part of the code. And now we say that our CFA has changed. Our CFA is now 16 bytes away from the stack pointer, not 8 anymore, because we've just pushed something onto the stack. And now we have the instruction to say that the offset, that register 3 is at CFA minus 16. So this is setting that cell at one row, at the next row on the table. And as we advance each instruction, we copy the previous rows down, okay? So everything in this row of the table is exactly as it was the previous row, but now we just, the advanced lock will basically advance to the next location, copy everything down, and then these instructions modify that particular cell, right? Next instruction is this sub. The sub does, where are we going? Advanced lock by 4, it's a 4-byte instruction. And then it changes the CFA again. And then we advance by 54 bytes, which brings us all the way down to this next instruction that affects anything that we care about for unwinding. And this does the opposite. So this is really just building up the table that we saw earlier on, instruction by instruction. And this is the actual raw binary data that you see in the binaries. But this is directly representable in the ELF image. But you can see this from this debug dump frames. All right.
So you just interpret that information when session throws, yeah?
So you only need to access this if you need to unwind the stack.
So it recovers the first information, then it includes those informations till the point to reach the same point at the IP instruction.
So
The IP register.
yeah, so in order to
have the original line, the line you had before.
Okay, well, I'll go through the whole lot. I'll try and kind of cover the whole thing holistically in a minute, but that's the point. Yeah. So you have the instruction pointer. From the instruction pointer, you can find the previous frame, including its instruction pointer. And from the instruction pointer, you can find this LSDA. So I mean, you can see the augmentation data here for the FDE is the actual table that we built up for the C++ side that we saw much earlier on in the assembly language output that said, here's the instruction pointers, here's the landing pads, here's the types we can handle.
Like instead of the static table, have delta to reach that. To that.
Right. So when you actually have to when you catch an exception, or when you unwind the stack from a particular point, then you have to run these instructions in order to find out how to unwind. Now, the result of running these instructions for a particular, so what I do is I need to kind of I have my instruction pointer and I have the start of the function. And I run my virtual instructions until the virtual instruction pointer matches the actual one. And then I have my state. Now, once I've done that once, I can cache that result. So if I'm presented with the same instruction pointer again, I can have a cache that says for this instruction pointer, here's how you get the table.
So if a function is bigger, too big, it's huge, the exception will be more expensive.
Potentially, yes. Yes, you will have to run more virtual instructions to get there. There are many other costs, so it may not be that much.
So one more reason to not try to big.
That's true. Just to say, Robert is saying it's another good reason not to write big functions because you have more instructions in the virtual system to run through. Okay, so that's kind of covered everything. So what I want to just do is walk through the code that actually does this. It's going to be a very high-level view of it, but just to actually see where the rubber hits the road. And just go through, as I was talking about Robert there, but just to go through the actual, from start to finish, what we need to do, okay? So at the point that we throw an exception, okay, we need to find the instruction pointer of the frame that called us, okay? It's part of the machine state. The initial instruction pointer is just sitting in the RIP or EIP register, right? From that instruction pointer, we need to find the ELF image that's loaded for that instruction pointer. And we need to walk to the linker tables in order to find that, right? So now we have the binary that provided the function that we're in. So from that, we need to find this EH frame section. Okay, and we're doing this every time we throw an exception. From the EH frame section, we need to find the FDE for the function that we're in. So there's the FDE will cover the instruction pointer. The FDE, remember, has a start and an end instruction. So somewhere in that is our instruction pointer. We need to find that. That'll probably be done with a binary search of some sort. So now we have the FDE. We initialize the call frames information with the CA. So what we do is we create a machine that has the first row of its, we create our table basically, and the first row of the table comes from the CIE instructions. And then we execute the instructions in the FDE, moving a virtual instruction pointer down as we go, as we advance locations from those FDE instructions. And eventually our instruction pointer reaches the actual instruction pointer we have. And now we have the unwind information, right? And this is the state for the calling frame, including the instruction pointer in that frame. And then from that, we can also find the LSDA information in the FDE. And this LSDA information is our C++ exception handling data. And we can look up our instruction pointer in that data in order to find out what code we need to run to either clean up or catch that exception. And then we repeat the process until we find something that actually catches the exception. Okay? So I'll pause if anyone got any more questions. There's a lot in that. Let me just leave that back up there. Everyone get all these steps?
Yeah, I'm just wondering, I don't know if it's related actually. Do you know if that approach is also taken by other languages, or just, I think just only compile language like
So your question is if that is done by other languages. So the unwinding information that we talked about in the EH frame section is all completely language agnostic. It's not C++ specific. So this will Go, for example, implements this. Doesn't implement exceptions, but it does implement this for stack unwinding. Languages that do implement exception handling, in theory, you can catch exceptions of foreign types in C++. So if you have a catch with ellipses rather than catch and a specific type, then a catch handler like that, in theory, can catch exceptions from non-C++ throws, whatever that would be. The caveat would be that for the C++ case, when you throw an exception, it's up to the catch handler to delete and clean up the exception object. Now, there's no way of doing that because it doesn't know what type the exception is, so there's no way of actually calling a destructor on it. And we'll see a little bit of that now in a second when I look through what the code does. Okay? Okay, so just to show us, this is kind of, again, a whirlwind view of what actually happens, so don't be too worried if you don't understand every single thing here. This is the assembly output for our H function that does our standard throw, okay? You can see we just basically said call random, and if random returns 0, we ignore, we don't throw the exception. So basically from here on is what we do to throw the exception. We allocate one. So the problem with allocating exceptions is we can't actually call malloc. We're unlikely to be able to use the stack because the exception handling may actually use more of the stack than we use ourselves. So we need to kind of have a special space to put our exception objects. So this is really just a call to a specialized version of malloc. I'm allocating an 8-byte object, right? I'm passing this destructor for this object into EDX. EDX is one of the registers used as an argument to a function later on. I move the V table for the exception into the first byte of the thing I've just allocated. So the allocate will return the object in RAX. So this is actually constructing the exception. It's an object with virtual functions in it. So it needs a virtual function table to be stored at the very front of it. And that's what this is doing. And then this ESI is the other register that I pass arguments with. And this is the type information for the exception. So this lets the exception handler know what type of object I'm throwing. And then eventually I take this RAX, which is the exception object itself, and put it into RDI. So the arguments that are passed to this CXA throw call, which is actually implements the throw, are in RDI, ESI, and EDX, right? So this call here jumps into this function here, which is the implementation that does the exception throw, right? So this is really just storing all of this information that we've provided. Things like where are we going? We have the object itself, gets stashed somewhere in here. Okay, it stores it in here somewhere. The type info, same thing, it gets put into this exception type. And then we have a destructor, which is just a function to call to delete the object, which we could see previously. We'll go back to the previous slide. We can see this is the destructor for it. Sorry, where's the destructor? This is the destructor here. So this is one of the arguments to the CXA throw function. So now we have the object, its type, and how to destroy it. We need to pass the destructor dynamically because the object may not have a virtual destructor. Okay. So from Robert's point, so at this point now we're going to have to try and unwind the stack. And the stack unwinding, as I said, isn't a language specific thing. So this unwind raise exception is what actually goes through the effort of unwinding the stack. Okay. And it gets passed in some information about the exception state, right? So this is unwind raise exception. Again, I don't want to go through the full details of it, but you can see that we're already doing things like talking about FDEs here. So we try and find the information about the FDE here. So this init context, for example, this is a pretty much setting up a context that has machine state in it, like instruction pointers and stack pointers and all the rest. We find the FDE here, this point. And if we find the FDE, then what we do is we get the personality routine, which was in the C++, which is the personality routine associated with this particular function. And we call the personality function routine directly. Okay, so this is calling the C++ provided personality routine. It's saying I'm searching for a handler. So this first phase is just trying to find the thing that will handle the exception. And then at some point, the C++ code comes back and says, I found a handler for it. If it can't find a handler, it'll pretty much terminate. And then what we do is we update the context as we go through each stack and each frame of the stack. And eventually, when we've actually found the thing that's going to handle the exception, we call this phase 2 version of it. And what phase 2 does above is, again, it just walks through the stack, and this time it calls the personality routine at this cleanup phase. And this gives the personality routine a chance to either clean up any of the objects that are on the stack or to actually handle the exception. And we get different return values. This install context means it has something to do. The continue unwind means just continue, I have nothing to do. And then once we call the function once and it tells us that it has something interesting to do, we pass control to it here with this update context. And this is pretty much like a long jump. And at the end of the code we saw earlier on, the thing that it did at the end of the landing pad for the cleanup function was it called this unwind resume. And unwind resume pretty much just lands us back into this raise exception phase 2 for the next frame down. Okay? And the last thing is just the personality routine itself. So this is part of the C++ runtime now that's getting the information from the unwinder, all right? And I won't go through too much of the details, but we can see that it's reading these ULEB data pieces of information, which is the information of that LSDA table. We can see it actually reading directly these entries in the LSDA table. Remember, we had a start instruction pointer, a length, and then the actual landing pad code here. This is way back, we saw these 3 values in that mapped particular parts of the code, right? And this CSLP ends up being put into this landing pad, and then way down later on, where are we going? Before we return, we basically put our landing pad into this context and say, okay, run this code. And then everything goes back and goes down to the next stack frame. So I know that's a lot of code very quickly, but I just wanted to show that some of it should make sense based on what we talked about already. Okay? Okay, I'm done. Anyone got any questions? My battery's about to run out.
You mentioned earlier about the the more simplistic ways of doing this. The last method you described here is what's used everywhere, right?
So this is what's used certainly in Linux. Windows, I think, has something similar. I don't know about the way it's structured. I know it has this structured exception handling from years ago, but I think it's actually probably more like SJ/LJ. But I don't know what things. I put it this way. I know at least on Linux there is, for the ARM architecture, they don't use these dwarf tables. They have their own special tables for some curiosity of the architecture.
It'll be similar in context.
It's very similar. So the function that when you're looking at the personality function there, I'd actually stripped out if-defs for the ARM case. So yes, it's very similar. It's implemented in the same function, but it's different enough that it's not dwarf. But it's only for the exception handling. I don't think the unwinding is affected.
This is all optimized for exceptions being very rare.
Exactly.
I haven't really used exceptions much, but if you had code that exceptions were used more often, would you possibly investigate a different tactic?
Okay, so just a question for anyone listening. The question is that it's optimized for the case when exception handling is very rare. I think there's a standard premise with C++ that if you don't use it, you don't pay for it. And that's kind of a driving force in the language. And as we saw, if you have functions that even don't throw or catch exceptions, if you use something like set jump, long jump handling, they incur quite a penalty. And even like throwing code across C function boundaries, for example, it just becomes impossible to do. So, I mean, if you did have an awful lot of exceptions being thrown, you could potentially go back to something that was more dynamic, that didn't require you to do all these table walks. But I don't think anyone wants to pay the cost for that. I mean, it was always envisaged, even when the set jump, long jump case had been put into GCC, that eventually they would get to a point where it was no longer required. So if it's going to happen frequently, it shouldn't be an exception.
Yeah, sure.
Okay.
Yeah, nothing coming up here. Anybody else?
Okay, guys, no other questions. I'm happy. All right.
Thank you.
Thanks for listening.